This video offers some help and hints for Problem 2-27 at the end of Chapter 2 in the 9th edition of Harris's Quantitative Chemical Analysis textbook. So this question, in so many words, says you want to prepare 500 milliliters of a 1.000 molar potassium nitrate solution at 20 degrees, but the lab and the water temperature is at 24 degrees Celsius at the time you prepare the solution. How many grams of solid potassium nitrate with a density of 2.109 grams per milliliter should be dissolved in a volume of 500.0 milliliters at 24 degrees Celsius to give a concentration of 1.000 molar at 20 degrees Celsius? And what is the apparent mass of potassium nitrate weighed in air is required? So I've restated this question a little bit. That's sometimes a good thing to do, is to restate a question in your own words. So we want to know, what is the apparent mass of potassium nitrate? So remember, apparent mass is what the digital scale on the balance shows you. What apparent mass of potassium nitrate would be used to prepare 500 milliliters of solution at 24 degrees Celsius gives us a solution with a concentration of 1.000 molar, so the 4 sig figs there, at 20 degrees Celsius. So this, it turns out, is a hard problem. So as your hints, let's draw some pictures, and sometimes when you're confused about a problem, maybe drawing some pictures will help you figure it out. So here's the picture we're going to draw. Let's draw a flask here. So here's a volumetric flask. I'm not too good at my artwork here, so excuse that. So here's a volumetric flask. So this is a 500 milliliter volumetric flask. So this mark here at the top is the 500 milliliter mark. Alright, so what we're going to do is we are at a temperature of 24 degrees Celsius when we mix up this solution. And so we are going to have this solution mixed up. We're going to have the meniscus sitting right here on top of the little line, marking line there. Alright, so what's going to happen if we were to cool this solution down to 20 degrees Celsius? Well, let's think about that. So here's that same flask again. So sort of looks the same. And again, it's 500 mils. And here we're at 20 degrees Celsius. And what the problem tells us is that at 20 degrees Celsius, we want this solution to have a concentration of 1.00 moles per liter. So what do we know is going to happen when you cool things down? So as we've talked about in class, things tend to expand or contract as you heat or cool them. So since we're cooling, this is going to contract a little bit. And so we're going to imagine that the new meniscus level is down here. So this is exaggerated, but let's imagine that the liquid has contracted a little bit, and now we have what looks like less volume. So it's no longer 500 mils because the liquid has contracted a little bit. All right, so that means what? How does this concentration right here compare to this concentration over here? Right, so the volume has changed. The same number of moles of KNO3 are in both flasks, so the moles of solute has not changed, but the volume has changed, and so that means that the concentration has changed. So since this is in less volume than this solution over here, what we expect is that this concentration is going to be higher than this concentration over here. So we expect this concentration to be a little bit less than 1.000 molar because we're concentrating it by shrinking the volume, just as though you might evaporate some of the solvent to concentrate a solution. So what you want to do is figure out what is the molarity of this solution. All right, so we want to figure out what is the molarity of this solution right here. So I'm going to call that X molar. So that's our unknown. So we're looking for that. Well, if you think about it, what's going on here, and this is a little more hint than, because I think this is a hard problem, so I'm not going to work it all the way out, but I'll give you a pretty good hint. So what we know is that the moles of KNO3 at 20 degrees Celsius has to be exactly equal to the moles of KNO3 at, I'm sorry, this is going to be 24 degrees Celsius over here, 24 degrees Celsius, and this is 20 degrees Celsius over here. All right, so those moles have to be the same. So the moles are the same. We can set up something that looks kind of like a dilution equation because the moles are the same. So over here at the 20-degree side, we don't know what the volume of this solution is, right? Because it shrank down a little bit from the 500 milliliters on the marking. So we don't know what that volume is. So let's call it Y. So we've got Y milliliters of solution. So we're using something that looks kind of like the dilution equation, and that's going to multiply the actual concentration of the solution, 1.000 molar. So we know what the concentration is at 20 degrees Celsius. Now over here in this solution, we do know the volume because we're right up here at the mark, and so it's 500 milliliters. But what we don't know is the concentration, X moles per liter. All right, so we've got kind of a problem here because we've got one equation and two unknowns. What we would really like to know is what is the concentration of this solution at 24 degrees Celsius that we're trying to make up. So we need to figure out how much the volume changes as we cool this solution down. So we need some way of solving for this Y variable. And so let me give you a hint. If we know we've got 500 milliliters at 20 degrees Celsius, then we can figure out how many grams of solution we have here, and we're going to assume that most of this solution is water. So we want to figure out how many grams of water we have here. So it's true that we've got some potassium nitrate in here, but we're just going to assume that it's all water. So we want the grams of water. And so to do this, we need to know the density of water at 20 degrees Celsius. And there's a table in your book that you can go and look up the density to a lot of decimal places of water at 20 degrees Celsius. I'm sorry, I keep writing 20 degrees Celsius. We're at 24 degrees Celsius when we've got 500 milliliters. So this is supposed to be 24 degrees Celsius. So you want to look that up and then figure out the grams of water. Now in going this cooling process, right, we're not changing the number of grams of water, we're just packing those water molecules more closely together because they're cooled down, they don't have as much kinetic energy, so they're not bouncing around as much, expanding their volume. So what we want to do next is then take this same number of grams of water and then using the density of water, but now we're at 20 degrees Celsius, we want to figure out how many milliliters you have at 20 degrees Celsius. All right, and so that's going to be this Y value that's right here. So once you know that, you'll be able to figure out what concentration of the solution you need to mix up. All right, so at that point, it looks like the last question that we worked, there's a video on that, question 2-23. So starting up with the molarity, which you will know, and the volume, 500 milliliters, you're going to figure out the grams of KNO3 that you need. Now remember, to do that, you're going to first go through moles. You're going to figure out moles and then grams. And this will tell you the actual grams of KNO3 that you need to make up that slightly diluted solution. And then like we did in problem 2-23, then you will calculate the apparent mass, M prime, from that buoyancy equation. So this is the actual mass, which is given the symbol M in the buoyancy equation, and you're going to calculate the apparent mass. All right, so those are the hints for that problem. Now go see if you can apply those hints and put together an answer for this question. Pause the video, and if you want to come back and check your work in a little bit, you can come back and watch me work out the solution. Okay, welcome back. So we're going to pick up where we left off, more or less. So we're trying to figure out how many milliliters Y of this solution we have after the water has contracted a little bit. All right, so we're going to use these values from the textbook. So put all these two pieces together. We've got 500 milliliters of water at 24 degrees Celsius. So at 24 degrees Celsius, the density of water is 0.997299 grams per milliliter. And so this will tell me how many milliliters of water I have, assuming my solution is entirely water, at 24 degrees Celsius. The next step is to figure out from this mass, the milliliters have canceled out. I now know the mass of water, the grams of water. So now we're going to use the density of water at 20 degrees Celsius. And so I know in every 1 milliliter at 20 degrees Celsius, there's 0.998207 grams. So you see the density of water is slightly higher at the lower temperature. The water molecules are packed more closely together because they're not knocking into each other as hard with as much kinetic energy. So the grams will cancel out, and this will tell me how many milliliters of water I have at the end. And so that number is, I'm going to keep a lot of significant figures here. So we have 7 significant figures in my density. I'm going to report this to 7 significant figures. So 499.5453 milliliters. So you see it is barely different than the 500 milliliters we thought we had, but it's a little bit. And so for precise work, we care about that. All right, so now I know my volume up here in this dilution-like equation, and so now I can calculate the molarity. So let's substitute into my dilution equation now. We've got 500 milliliters. We're looking for the molarity of that solution, x molar, and that equals y milliliters, which is now 499.5453. Actually, I should round this 3 to a 4 because the next number in my calculator was an 8. So 5454 milliliters times the molarity at 20 degrees Celsius that I'm looking for is 1.00 molar. Okay, so we solve this equation, divide both sides by 500, and do the math, and we'll figure out that the molarity of the solution that we want to make up at 24 degrees Celsius is 0.999098 molar. All right, so again, I'm carrying more digits than I actually would be warranted according to significant figures, but I will round at the end of my calculation. All right, so we're not making up a 1.000 molar solution. We're making up something that's barely different than that, right? A little bit different than that. So now we need to figure out the next step. How many grams of potassium nitrate I need. So for that, we're going to start off with our 500 milliliters again. So that's the volume of the solution, and I'm going to convert that to liters, 500 liters, and then we multiply that by the molarity, 0.999098 moles of potassium nitrate in every 1 liter. And then I'm going to use the molar mass of potassium nitrate, 101.103. grams per mole, to perform the next step where I convert into into grams. And so when I'm all done, this tells me that I'm going to need to weigh out 50.506 grams of potassium nitrate. So that's the actual mass. I now want to know, well, what will the balance actually read if I'm weighing out that amount? So I'm going to solve the buoyancy equation for m prime. So m prime is equal to m times 1 minus the density of air divided by the density of the potassium nitrate divided by the quantity 1 minus the density of air divided by the density of the calibration weight. And so we know what all those numbers are, so we just plug them in. So the actual mass, 50.506 grams, times 1 minus the density of air, 0.0012 grams per milliliter, divided by the density of the substance, so the density of potassium nitrate, 2.109 grams per milliliter, We divide that by 1 minus the density of air, again, 0.0012 grams per milliliter, and divide by the density of the calibration weight. It's stainless steel, 8 grams per milliliter. All right, so when we're all done with this calculation, we will get an apparent mass of 50.485 grams of KNO3. All right, so fabulous. So this is the final answer. This is what you would actually want your balance to read if you wanted to make up a solution that was exactly that was precisely 1.000 molar at 20 degrees Celsius, even though you're at 24 degrees Celsius. Just for comparison, if you had just assumed that there was no difference in temperature and hadn't worried about this apparent mass business, what you would have calculated to make up a 1 molar solution, 500 milliliters of a 1 molar solution, you would have gotten a mass of 50.552 grams to make up that solution. So notice that they're close but different. So for precise work, you might need to know that. Now, as just a final parting comment, I would say that we would never ever do this problem in a practical setting in a lab this way. So it would be very rare that you would need to have a solution that has a very precise concentration at a particular temperature. Now, what you might want is to know very, very precisely what the concentration of your solution is. So probably you don't need a solution that is 1.000 molar potassium nitrate. You probably do need a solution that is around 1 molar, and you need to know precisely what it is. And that's a very different problem and a much easier one to tackle in the lab. So thanks for watching.